Welcome back. We are getting close to the end of chapter 6. We are going to talk just a little bit about work. Work is a type of energy. It's the amount of energy it takes to move something. That's either against gravity or that's along a table to push something that's on wheels, maybe. That all involves work. And our definition of work is going to be the force times the distance, meaning F times D. And D often will just be X for us. Now, when we talk about force, this is usually mass times gravity when we're working against it. Now, and this is when we are when we have a mass and a gravity, the mass will always be in kilograms. That's the standard unit, or the metric unit, pardon me. And that'll always be multiplied times the distance, which will be in meters when we're in metric. Now, it's a little different when we're dealing with the American system, because F is just the weight. Which already accounts for gravity. So mass and weight are not the same thing. They can be translated on Earth relatively easily because gravity is the same on everywhere on Earth. And this is going to be times another distance. Often it's in feet. So our work will be in foot-pounds. Now, if F is measured in newtons, this is going to be this one here. Let's put a little color here. If it's measured in newtons, that's capital N. That'll be this one here. And the distance is measured in meters. Then the resulting work is called a joule. This is for those of you who have not taken a physics course before. A joule, and we represent a joule with a capital J. And as I said before, if we're in the American Standard, then we are often in foot-pounds. All right, so let's jump to it. The work done by moving an object from A to B this is work. Now, it's force times distance, but what I want to do is I want you to think about if you have a heavy cable that's hanging off the side of an edge. When you go to pull that cable up, you have to pull the entire weight of that cable up. But every pull that you pull up, it gets lighter and lighter because less of the cable is hanging over the edge. So if you break that down into infinitesimals, the dx's and stuff like that, what we're going to end up with here is from A to B, f of x dx. And this is where f of x is the force function. What we're talking about today, we're going to do a very, very, very basic element of that. But you can imagine it gets super complicated, as does everything. So let's do an example. A particle is x feet from the origin, and a force, and they give us the force function. In the other example that we're going to do, we're going to have to build our function. F of x equals x squared plus 2x is applied to it. How much work is done on the object as it moves from 1 to 2? Now, they're not giving us any units here either. Well, the work is going to go from 1 to 3 of x squared plus 2x dx. It's that simple. Not a lot of work for this one. Pardon the pun. X squared from 1 to 3. So this is going to be 1/3. 3 cubed is 27 minus 1 cubed, which is 1, plus x squared. So 3 squared is 9 minus 1 squared, which is 1. And I'm going to show you a fancy trick once again. So 26 divided by 3 plus 8. And I'm going to convert it using the math button into a fraction for me. This is going to be 50 over 3 joules, foot-pounds. We don't know what this is as far as the unit goes. All right, Hooke's law states that the force required to maintain a spring stretched x units beyond its natural length is proportional to x. So it says that the force to stretch, now it says stretch or to compress a spring, it's the same physics, is proportional to the distance that it gets moved. So picture this, you have a spring and you're stretching it, and the farther you have to stretch it, the more energy you need to stretch it. So this is going to translate for us. We're going to put a constant proportionality in there, where the force is equal to a constant proportionality times x. And we're going to need to solve for that proportion constant. All right, example 2. A force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is done stretching the spring from 15 centimeters to 18 centimeters? Okay, let's start here. We have a spring. Its natural length is 10 centimeters. To stretch it to 15 centimeters, it requires 40 newtons of force. Now, because we know that it's proportionate, we're going to say that the force 40 is equal to the constant proportionality times 15. Pardon me. Now, I want to be clear, this needs to be in meters. So we are stretching it a total of 5 centimeters, which is 0.05 meters. So dividing that out, I'm going to get that K is equal to 800. So my force is equal to 800 x. Now this is where, so our 0 is the natural length. So our integral, our work, is going to be the integral, and we're going to go from 5 centimeters to 8 centimeters from its natural length. So we got to be careful with these boundaries. Now these are centimeters, and we're mixing and matching right now. So in reality, again, these are in centimeters. So we're going to have to rewrite this. So now let's integrate. I'm going to get 1/2. That's going to chop that down to 400 x squared from 0.05 to 0.08. And let's see what we get. 400 times parentheses 0.08 squared minus 0.05 squared. That gets us 1.56 joules. And that's about as in depth as we're going to get for this particular class. I hope that helped.